Hello, everybody. Good to see you all. Welcome to episode number 35, Kubernetes Topology Aware Routing at Cilium. So we're going to be playing with a relatively new feature in Kubernetes today. We're going to show how to deploy Cilium and Kind on a cluster in such a way that the topology aware stuff can be used. And then hopefully, if all things are equal, we're going to get to a place where we can actually even see how some of that actually functions under the covers. We're going to play with all of that stuff. So looking forward to it. I hope that you are as well. I'll jump over here to the comments. I have two screens set up. The one that I'm going to be doing all the work on is in front of me, and your comments will be on my right. So if you see me looking over there, it's good to see if you're with me, if you're checking me out. So if you're in the audience today, definitely say hello. I can raise you up in the stream, and then we can see your awesome voice. But yeah, I also just let me know if you can hear me, if you can see me. All of those things are working well, and we'll keep moving on. All right, let me add this to the stream. So these are our notes, and you can get to our notes by going to that link right over there on the bottom, show notes, hackmd.io/echo live. This is episode 35, so you'll see a link there on that website that takes you to episode 35 notes. I'm going to end up putting all of my manifests and everything into this notes file. So if you want to reproduce everything that I'm playing with, that's actually one of the goals of these shows for me, is to set up environments in such a way that like people other than me can kind of explore these things, because for me, it's about sharing the knowledge, and so hopefully at the end of this, if you're interested in playing with topology aware hints, it is a relatively subtle implementation of a tool. If you want to play with it and see how it works and see if it works for your particular use case, and this should get you far enough along that you'd be able to actually do that work. This may end up being, as a heads up, two episodes. The first one this week, of course, and the next one like maybe a week after next. But it's good to be back. It's good to see you all. Let me know if you're out there. Great to see. Great that we're making this all happen. So this week, so I'm going to jump into it here. So our docs, this is a feature that is in topology. It's called Topology Aware Hints, and it's a different feature than the previous implementation. And we'll look at the KEP here in a second to understand a little bit more. But there was another topology aware solution that ended up being phased out in favor of this one, and I'm sure that the KEP gets into why. But the bottom line is, the goal of this, the motivation behind it, which I think they've captured pretty well in this blurb, is basically in a lot of environments, it's possible to say, like if you're in AWS or in any of these environments that give you multiple availability zones per region, there is a cost associated with moving your data between those availability zones, right? Or maybe you're actually deploying Kubernetes across not just availability zones, but also across racks and rows in a data center or ASs or what have you. And you wanted to actually ensure that by default, particular services that you define will route traffic within a particular topology or a particular zone. And the benefit of that could be that you're just trying to keep all that traffic within that particular chunk of the network, of the underlying network space. You're trying to keep that traffic within the particular availability zone in AWS rather than allowing it to traverse. But you have other nodes and other zones to catch if there's no way to actually do it. But your goal is to basically try to constrain traffic as routed by a service to a specific topology aware kind of model, and make sure that traffic, as again managed by that service, would be hosted, would only consider those endpoints that are available within the same zone as you've identified as necessary for that service. So that's what we're going to be playing with. It should be a fun one. So let's talk about what the setup looks like for me, and then we're going to start playing with things, get things deployed. So what I've got so far is I've got this kind config here, and we'll just talk through it real quick, and then we'll move on to kind of the fun parts. There are a couple of really interesting things here at the top in the kind configuration, and these are available as part of the kind project. And if you are unaware, if you have somehow managed to never see me present on kind or check it out yourself. If you go to kind.sigs.kh.io, you come across a really interesting project that allows us to spin up multi-node clusters leveraging Docker. So your Kubernetes nodes are going to be Docker containers, and we're going to use kubeadm as the cluster initializer, if you will, the cluster configure part. And that means that there's quite a lot of configuration that we have control over. Now, Kind was originally developed to be a part of the testing for Kubernetes. Like that was part of the original goal, was to make it so that we could test all of the code of Kubernetes itself a lot faster and a lot more efficiently than waiting for a bunch of VMs to spin up and then deploying software onto them and then seeing if they form a Kubernetes cluster and then testing that one feature that you're interested in. The benefit of this is that we can do that code level testing with just Docker containers, and as you can imagine, it's much faster. There are some caveats. There's some things that we can't test with Kind, like we can't test things like, secret memory handling. We have to make the assumption that we have one Linux kernel that is actually shared across all of the nodes, rather than one Linux kernel per node. And so there's some caveats and some interesting things there. But for the most part, if you're testing functionality like what we're going to test today, then Kind is great, and you should definitely check it out. All right. So in my topology, I've got a few nodes defined. I've got my control plane node. I'm just going to go with a single one for now. I've got about 6 workers. Each of the workers has this join configuration, which is an artifact of leveraging kubeadm to do the initialization of these nodes. And I can pass different arguments to the kubelet itself. And so when the kubelet gets instantiated on these nodes, I'm going to pass another argument saying node labels, and then I'm going to set a topology. So 2 of my nodes will be in zone A, 2 of my nodes will be in zone B, and 2 of my nodes will be in zone C. Up here at the top, I've done a few other interesting things. I've enabled the feature gate for topology aware hints. This is necessary because it is a beta feature. And then in the networking section, I've done a couple other things. I've disabled default CNI, and that means I want to deploy my own CNI solution. And I've also done kubeproxy mode none. And kubeproxy mode none means that kubeproxy will not be deployed into this cluster. Now that's important because part of my other goal here is to actually explore topology-aware routing in Cilium. So we've just recently, as of the 1.11 release in open source Cilium, we've announced topology-aware load balancing. And this diagram looks kind of like what we're going to try and set up here today, right? We've got multiple zones. We got zone A, we got zone B. We're going to deploy a client pod probably into zone A, but could be into any other zone. And then once we get that deployed, we're going to try and make sure that the client pod only accesses those components within the same zone as it's residing inside of. And so we're going to try and recreate this example, this experiment. Now to do that, that means that we need the way that topology-aware hints work is it affects 2 different components within the Kubernetes stack. The first component is the endpoint slice controller, and that is the thing that actually instruments those endpoint slices with hints about where to go for particular traffic, like which endpoints to consider when defining that load balancer configuration. And then the implementation side, like now that we have the hints, we've instrumented the service in such a way that whatever is going to implement that service can go ahead and can take into account those hints and do the work. That is actually usually done in most Kubernetes clusters by kubeproxy. So kubeproxy would see those hints associated with that service, and when defining its IP tables rules, it would actually take into account those changes. In our case, we've made Cilium do this work, and that means that we need Cilium to operate the kubeproxy piece, because it's still a part of like how those service definitions are defined. If we use Cilium to replace kubeproxy, and Cilium is topology aware, then we can expect the same sort of functionality to leverage topology aware hints in a service that we defined where Cilium is the one that's doing the kubeproxy work. And as we dig into this, that's what we're going to play with. We're going to see how that works. We're going to kind of like show underneath the covers, and maybe even show like some of the configuration on a Cilium agent where we see that load balance, where we see that load balancer configuration. All right, that was a lot of talking. It's a big info dump, but let's keep going. We have a lot to cover, and I would really love to get through this, at least most of it in this first hour, maybe even all of it. Maybe we'll see. All right, so in my configuration, like I said, I have disabled kubeproxy, and I don't have any CNI deployed. So let's go ahead and do kubectl config use context. If we look inside of here, we can see exactly kind of what we were expecting to see, which is a Kubernetes cluster, get nodes, show labels. So there are all of our nodes, and we can see that we have this topology key, and it was actually correctly associated with the node itself. So we could do things like get nodes -L topology key zone A, and that would be those two, and B are those two, and C are those two. So the first two are A, the second two are B, and the third two are C. So that's actually working kind of exactly as we had designed it. And if we do kubectl get pods-A, we can see there is no kubeproxy defined, right? We have the usual suspects. We have our API server, our controller manager, our scheduler, our etcd, a couple of core DNS pods, which are waiting for somebody to do something on the back end to make it so that they can actually be provisioned. So we need a CNI before that will happen. And the same thing for the local path provisioner, which is our local storage inside of a cluster. So next thing we need to do is we got to deploy Cilium. So let's go ahead and take a look at how that's going to work. So my goal is to actually deploy Cilium in such a way that we can replace kubeproxy. And so here is an example of how to do that. So I'm going to go ahead and copy this example down and drop it into our and then this will be our configuration. And there's a couple of interesting things. And if you read into the docs, you're going to learn a little bit more about this. But since we're trying to do kubeproxy replacement, we want to set this to strict. We want to ensure that Cilium will do all of the things necessary to replace kubeproxy. Next thing we're going to do is we're going to set our K8 service host, and we're going to set our K8 service port. 6443. And then the service host piece is interesting. Let's talk about that for just a minute, and then we'll move right past it and keep playing here. So the K8 service host is important because usually when you deploy Cilium or any other CNI, it comes up in a host port kind of or host network kind of mode, right? And as part of its configuration, it's given a service account. Inside of that service account's definition, it's actually it's usually defined as part of the way, not in the service account definition. When something like a CNI agent is going to interact with the API server, it's going to use client Go to actually do that work. And if it's being deployed within a cluster, one of the things it will do is assume that it can talk to Kubernetes.default. SVC. That Kubernetes.default.svc is implemented by kubeproxy, right? That is the internal representation of the Kubernetes API server. And for the most part, that's totally fine. It completely works, right? I mean, if you just do a Cilium install using the Cilium CLI, or if you use Helm to do this install, it'd be fine. But in our case, we don't have a kubeproxy. We have disabled it. And so the challenge is that we need to figure out some way to tell the Cilium agent where, what to go talk to be able to interact with the API server. Now, we've had to solve this problem before when we created this cluster, right? all of the kubelets on the worker nodes had to talk to the API server to register themselves. And we can see already that that's working, right? If I do kubectl get nodes, I can tell already that there is some way to address that API server. And then we need to kind of look into how that's done. Now, the benefit here is that we can do, because these are Docker containers, let's just jump into the Cilium control plane node. One of the things about kubeadm is that on a control plane node, it lays down an admin.conf. And that admin.conf gives us a view of how the cluster is configured in such a way that the kubelets can communicate with it. This admin configuration is my kubelet configuration to interact with this cluster. It lives the life of the cluster, and as soon as I tear the cluster down, these credentials will no longer be relevant. But inside of here, we have the server line. And that server line actually tells me how all of the kubelets are interacting with the API server. So on each of the kubelets, they're actually addressing the API server at HTTPS Cilium-control plane :6443. And in my case, I want to go ahead and populate that same server line inside of here. Just one. Look at our docs here real quick. It says replace with API server IP. I think it's just the name it wants. So let's just go with Cilium control plane port 6443. Okay. Now there's a couple of other things we need to enable. Now it's already configured in the cluster, or sorry, it's already configured in Kubernetes to enable the endpoint slice controller because we have enabled that feature flag. But now we need to tell Cilium to do that as well. So if I do a search in the Cilium documentation for topology aware hints, this is the feature that I want to enable. It says the kubeproxy replacement implements the K8 service topology aware hints. This allows Cilium nodes to prefer service endpoints residing in the same zone. To enable this feature set load balancer dot service topology equals true. Go ahead and do that. There's one more thing I want to enable here. You know what, I'm going to look up the value for this. So let's do that together real quick. So since we're using Helm to do the install, I've seen no comments so far. I'm wondering if you all are out there. Anybody out there with me? Hello? Show values. Cilium, 1, 11, 11. Oh, there's actually even, oh, that's cool. There's even so it's part of load balancer, no doubt. Yep. Load balancer, service topology, true. Hey, Yuka, good to see you. How are you doing? Can you all hear me okay? I'm glad you're out there. So the other thing I want to do is I want to set my IPAM mode. IPAM mode. I didn't do it right. IPAM mode. Kubernetes. I'm doing that because I did not change anything about the way that Kubernetes is configured, and so it's already picked a CIDR, and so I'm actually just leveraging that same CIDR already here. So I'm going to go ahead and actually install Kubernetes directly because that's going to work better. All right, so here we got our install configuration. We're going to throw it into the kube system namespace. We're replacing kube proxy. We've set the Cilium, the K8 service host. We've set the service port. We've enabled load balancer service topology equals true. We've set our IPAM mode to Kubernetes. Should be everything we need. Give it a whack. See what happens. Looks like there's something in my configuration that is complaining about topology key or a label that will eventually be removed. Some annotation stuff. Probably this stuff here. So I'll have to look into that. Do a W here. Let's see how far we get. Cilium operator is running. While this is happening, I'm going to grab a function from another machine I had set up here, which I thought was super handy, and I just forgot to grab it over here real quick. So do that. Created this function to do some testing on another thing recently, and it was really handy. I think I'd like to have it running inside of my regular system, so I'm going to grab a new tab. And what this will do is it's going to this gives me the ability to basically just create a super simple command or here. And then, you know what? I need one more argument here, don't I? Yeah. I need. I could just use this argument, the second argument already. Yeah. Okay. But here's what this is going to do. This is a kind of an interesting little hack. And what it's doing is it's creating a pod directly. And I'm setting the labels and the name for that pod also somewhat directly. And so my goal here is to make it so that when I create this, I should have the ability to go. So should be able to create a pod on any node by giving it this command, this function, echo pod, and then the node name. And then when it create it, it will assume the node name, and it will assume the, I will set a label saying what the node is, and then I will also set the name of the pod, and I will also make it part of an app echo. And that benefit of that is that when I now deploy these pods specifically to nodes, I can actually play with balancing. I can deploy more of them to one node or less of them to another. And this gives me the ability to be really give me a lot of really fine-tuned control about how we deploy things within our experiment here. Because as we get into this feature, we're gonna come across the fact that it's actually somewhat sensitive in the way that it actually does this work. There are a lot of caveats about how it will apply the service topology hints, like, based on particular criteria. And so we're going to play with that a little bit. But having a function like this that gives us the ability to put more nodes wherever we want them, I think that will come in really handy. Here, take a look at our configuration. Looks like things are working pretty well over here. Pods-A. Hey, so it worked. We have things working at all. So then we'll just do Cilium config view. What Cilium config view does is it lets me look at the configuration of the cluster here. And so what I'm looking for I'm looking for this particular value here, which says enable service topology equals true. And so now what we've got is we've got a Kubernetes cluster configured. We've got our Cilium configuration configured. We have, I think, everything we need to actually play with service topology within the cluster here. And so, I'm going to go ahead and do a source of my configuration that I just made, kube functions. And then in theory, I should be able to do echo pod. Look at nodes. Pod. Cilium worker. Two. And then the benefit of that, if I do -o wide here, is that I'm able to deploy those pods directly to that Cilium worker. I can actually even address them by name. And so that's actually pretty handy for me. So I can actually understand that these pods are in here, and I can see based on the IP address that my IPAM mode is Kubernetes. So that's working correctly. Everything is doing pretty well for me so far. A little bit about the echo, the inanimate echo server. This is actually a pretty handy tool. Let's just jump in. So, okay, add curl, and I don't have any services defined yet, so let's go ahead and do that. Service. Oh. Something that's been bothering me for a little bit. And here, if I do a kubekittle create service echo, I can give it a name, but there's no parameter selector. Yeah. Create service, but there's no like other parameters, which I think is kind of a bummer. Service echo -o run. Weirdly, that actually works out. So it makes the assumption that the selector is app equals echo, and I believe that will work for us. Equals echo. Yeah, totally works for us. Okay. So we can go ahead and create our first service. Let's get rid of that dry run. SVC. All right, so now we should be able to do curl echo.default.svc. Perfect. Okay. So this is what the Echo server does. It's actually pretty handy. So basically, it's a tool that lets you kind of have a view of what's actually. It gives you, it like prints a bunch of the headers out, right? So we can see what the host name is for the thing that we're interacting with. We can see the requesting IP address. This is the IP address of the pod that I'm actually making a call from. We can see the request headers. Like this was actually just a request to echo default.service, which was what you just saw me type in. And then inside of here, we can also see the environment. We can see the any environment variables that have been configured for these pods. Alrighty, so that's actually pretty handy. So we can actually see that we're a part of Cilium Worker 4, and let's take a look at this real quick, just so we can understand whether we even have anything topology-wise working at the moment. So if I do kubekittle get pods -o wide, my bash pod is running on Cilium Worker 2. And Cilium Worker 2 is part of Zone A. And Cilium Worker 4, which is the thing I'm talking to, is part of Zone B. Nope, yeah, Zone B. So Zone A is Worker and Worker 2. Zone B is Worker 3, Worker 4. Zone C is Worker 5, Worker 6. So at the moment, this is just working like any other Kubernetes service, no topology hints or awareness at all, right? It's just basically connecting me to the back end of another service, right? And there's no IP tables rules, right? So there's no IP tables rules associated with this route. We're actually using Cilium for this. So Cilium is doing all of the kube proxying, and we can take a look at that real quick and kind of like just talk about how that works. So exec ti-n kube system. Let's take a look at system agents. Cilium list. Host. Echo default service. Add bind tools. So 1096.153.38. That's this guy here. And this is the load balanced implementation inside of Cilium, right? So I'm looking at the load balancers that have been configured by Cilium, and these would be all of our services. And so we can actually see in here, this is actually the configuration. So all of these are the healthy endpoints behind that service, and it's considering all of them. Pretty cool. All right, yeah, do anything. Oh, yeah. All right. So now the next thing I want to play with is getting this service topology stuff working correctly. So far what we've covered is we've got our cluster deployed, we've got Cilium deployed in a topology aware model, we've got the cluster deployed in a topology aware model. Looks like, yeah, we have our basic service set up. Things are working. We've got a balanced configuration here. So let's go back to our docs. Yeah, let's dig into it. So we talked about the motivation. You can activate topology-aware hints for a service by setting the service.kubernetes.io topology-aware hints to auto. This tells the endpoint slice controller to set topology hints if it is deemed safe. Importantly, this does not guarantee that hints will always be set. How it works. So this is coming from the endpoint slice controller. That's the thing that's actually going to do this annotation that we were talking about before, like what the hints are. And then in kubeproxy, or in our case Cilium, is actually going to take those hints and define the routing behind them. Now this is what I meant by the subtlety. So this is the piece right here where it says safeguards, where things get pretty interesting, because there are a number of interesting safeguards, like the insufficient number of endpoints and impossible to achieve balanced allocation. Like if zone A is twice as large as zone B, but there are only 2 endpoints, an endpoint allocated in zone A may receive twice as much. The controller does not assign hints if it can't get this expected overload value below an acceptable threshold for each zone. Importantly, this is not based on real-time feedback. It is still possible for individual endpoints to become overloaded. And I think what that means is that when there is a syncing mechanism wherein like it will try to resync over time and change the state, but it may still be possible in between those syncs to overload the configuration. It says one or more nodes has insufficient information. If a node does not have any topology awareness zone label or is not reporting a valuable for allocatable CPU, the control plane does not set a topology aware endpoint hint. So kubeproxy does not filter endpoints by zone. One or more endpoints does not have a zone hint. Filtering endpoints for a service in this state would be dangerous, so kubeproxy falls back to using all endpoints. A zone is not represented in hints. If kubeproxy is unable to find at least one endpoint with a hint targeting the zone it is running in, it fails to using endpoints from all zones. So it looks like based on all of these constraints, like all of these safeguards, like it always falls back to just using all of them. There's also some constraints. So either external traffic policy or internal traffic policy is set to local on a service. It is possible to use both features in the same cluster on different services, just not on the same service. This approach will not work well for services with a large proportion of traffic originating from a subset of zones. Instead, this assumes that incoming traffic will be roughly proportional to the capacity of the nodes in each zone. The endpoint slice controller ignores unready nodes. endpoint slice controller does not take into account tolerations when deploying calculating. This may not work well with auto scaling. That makes sense, yeah, because like you could actually again kind of throw the balance out of whack again. All right. Well, let's go ahead and try to annotate our node with this annotation. Sorry, our pod, our service. Let's jump back over here. Kubectl, annotate, service, echo. Oh. What this should do is it will annotate that service Kubernetes.io topology aware hence equals auto. Kubectl get endpoints. Slash A. Hey, look at that. Very cool. Okay, so what we see now in this configuration, let's go ahead and just do a refresh. What we're able to see in this configuration is that for the endpoint slice associated with our echo service, inside of these, we have our list of endpoints, right? And so here is an endpoint hosted on Cilium Worker 4. It's 4 zones, zone B. It's in a ready state, it's serving, it's not terminating. And then we can go down and we can see all of the others. And so here is our hinting, 4 zones. 4 zones. So that seems to work pretty well. Our next step here, well, let's try and do our curl again. We're still bouncing all over the place, for sure. See what else there is to do about this configuration. Let's go ahead and check our allocatable. Yeah, so we're definitely getting an allocatable CPU. Let's see. go back to our notes here. So one thing I did notice was I did find the tests for this. So this is the adding support for topology aware hints to the endpoint slice controller. And that's the feature flag getting enabled. It looks like the endpoint slice controller is doing its bit. But what we're not seeing is this is all the test code for actually writing up the test for the configuration of the endpoint slice system, which seems to be working. Like that does seem to actually be populating just fine. So no issues there. So maybe what I want to look at is topology. Now I'm looking at the tests for this stuff. These are different load balance configurations. Endpoint slices. Check in to see if the load balancer understands the configuration. Service cache endpoints. Testing the service cache. Let's do a search for topology. Okay, so we have our service. We have topology aware, hence auto. We have our cluster IP. It's all right. Yep. Zone A, zone B. Enable service topology true. Test service endpoint filtering. Well, test makes sense. It looks like the configuration is set correctly, so enable service topology is definitely true. Check if the configuration of the service is wrong. If SBC-OEL. Internal traffic policy cluster, so that's fine. Service Kubernetes IO topology where hence auto. Got all this configured correctly. Let's see what I'm missing here. Enable service topology. And that's definitely what I see on this side, right? Big crap. Topology. Enable service topology, true. Definitely making use of endpoint slice. That's a different output than last time. So from Cilium Worker 3, what am I looking for? So what I'm looking for is what's that about? Okay, get, yeah. Wide. 153.38. This is 153.38. Why does it have 3 endpoints in it? Should it only have 2? One, 2, 3, 4. So I should have 4 actually. But I see 3. But it is interesting though, because those are actually, so if this is Cilium Worker 3, and that means I should only see those things associated with 3 and 4, which are right. Yeah, so that's actually right. So defining the service so that it will, oh, there's the 4th one. I do see all 4. So that's the service, defining the service such that it will only route over these 4 endpoints. which seems like it's configured correctly, taking into account the configuration. So if we do get pods dash again dash O wide, we look at our test pod. Our bash pod is on Cilium worker 2. kubectl get pod dash n kube system dash O wide grep worker 2. Cilium. See how that's going to Cilium is. Cilium get LB list. Yeah, it's configured correctly. So into my pods, curl default.svc That is neat. Something else must be routing me, but I'm not sure what. Neat stuff. It appears as though I'm falling back, but I haven't figured out why or how. According to this configuration, I should be actually balancing over these pods, but I am not. What if I did it by E? That's cool. Cilium service list. Cilium. Let's look and see if there's something else happening. Worker number 2, so we do Cilium worker. Yeah, definitely not happening here. Cilium Hubble port forward. Cilium Hubble enable. Yeah, I do see it. I do see it in the config, right? Because if I thank you, Greg. The question was whether the configuration took, right? So Cilium config view grep topology. I do see it set configured correctly, and I do see the artifact of that, which is that the load balancer in Cilium is configured in such a way that it appears correct. But what I'm seeing is on the data path, it's definitely not doing the thing I expect. And so looks like we may have discovered a bug. There we go. Hubble port forward. Hubble observe. Settle down. It is lunchtime here in California, so I'm going to take off and go enjoy lunch with the company. But I look forward to our next episode where I'm going to dig further into this and see if we can figure out what's actually happening. So tune in 2 weeks, and we will revisit this topic and dig even further into it. In the meantime, I hope you have an amazing weekend. Just really enjoy yourself out there as much as you can. Get out, get some fresh air, and enjoy yourself. And I will see you all next time. Thank you so much for tuning in. I hope that this was a fun episode for you. I'm going to put into our notes all of the configuration that I've got set up here so that we can play with it. And I'll see you soon. Talk to you later.